Welcome human biology class. This is the skeletal system video lecture number 2, and I thought I would start off. We're actually talking about bone growth today specifically, and so I thought I would start off with a biblical passage out of 1 Samuel 17. It says, "Now the Philistines gathered their forces for war and assembled at Soco in Judah. A champion named Goliath, who was from Gath, came out of the Philistine camp. He was over 9 feet tall." That would be an impressive look, and it goes on to describe his armor and things of that sort. Here is a gentleman named Robert Wadlow, and he's from, I think it's Alton, Illinois, and he is, in this picture, 8 feet, 11.1 inches tall, so sort of a Goliath type of a guy. He suffered from a condition basically relating to an overactive pituitary and overproduction of human growth hormone. He died at age 22. He died actually of a blood infection from a leg brace that had irritated his skin, as I understand it. But at the time of his death, age 22, he was still growing. So he could have reached Goliath's height. He was very close to it at that. Another interesting thing is, if you read reports, this gentleman, although a very kind, gentle person, was incredibly strong. And so it's kind of interesting to see what that might have looked like. Normally I start this section asking the class, who has grown the most in a year? Or even, do you know somebody who has grown an incredible amount in a year? And it's common for the class to come up with somebody that they have experienced that's growing 6 inches in a year. 3 inches is normal, but then I'll ask the age of that person, and generally it comes back somewhere in the early teens or mid-teens is when those incredible growth spurts occur. Humans tend to grow not sort of steadily day by day, adding a little bit and a little bit, but in spurts that may occur in as short as a few days. Some would even argue overnight you can grow measurably. There's some evidence that would lend some credibility to that. I don't know, but I know it's an interesting thing to study. So that's what we're going to look at today. So really, when it comes to bones, I'm going to switch images here. Back to this image from your textbook. We're looking at bone. Last time we looked at the cellular structure of bones, the osteons, the osteoblasts, osteocytes, osteoclasts that make up bone. Also highlighted the blood supply and nervous tissue that's in bones. Okay, and we're going to end up today talking about cartilage, and you'll notice there's some distinct differences, basically lack of a blood supply in cartilage here. So first of all, when we talk about bones, bones tend to add length at what's called an epiphyseal plate. So if I go to another image from your textbook, right here, this is a developing bone inside the womb, and then as they grow, we can see that there is basically a cartilaginous skeleton that bone grows around. So we start out with cartilage, very flexible, and then bone develops from that. And you'll notice here that a blood supply begins to invade that developing bone. There is not a blood supply, again, when it's cartilage, so that's an important point to remember. And there are these sort of growth centers at the ends of bones. In the case of this, looks like a humerus, multiple growth centers at these ends of these bones. If we look at those in a little more detail, or up a little more closely, we can see there are distinctly different areas that are created. So really there's a new area of cartilage in a developing bone. I'm looking at your notes now. And really, right here at an area called the epiphyseal plate, well, actually here they use the term epiphyseal growth plate. You probably have heard of growth plate. There's the epiphyseal plate. This is where growth actually occurs. This is where the bone lengthens. It doesn't lengthen evenly over its whole surface, but at these growth plates. And what's happening right here, these are areas of cartilage. And those areas of cartilage expand rapidly. So if we look at this area more closely, like we see over here, we can see that there's a proliferating zone. Proliferating zone means the cartilage cells are rapidly dividing. Degenerating zone doesn't necessarily mean they're rotting away, if you will. It means the cartilage cells are basically dying back, but they're being replaced by bone cells. Bone is invading it. And so there's this constant battle as a person's bones lengthen. This growth plate, cartilage cells reproduce and reproduce, and they stretch that bone right here. But as the cartilage cells are reproducing, bone cells are invading them and shutting down the growth, if you will. But that's okay, because at the other end of the epiphyseal plate, more cartilage is being developed. And then back down here, bone is invading it. And so the bone grows as that complex battle goes on. It's not unlike, I'm going to try another video clip from YouTube here, so we'll see if I get banned on this one too. It's not unlike Lord of the Rings, Army of the Dead, the battle for Plenner Field. If you remember this particular, whoops, that is not what I wanted. If you remember this particular battle, if I can get to it, there we go. Watch what happens. Okay, a little ghoulish, I'll grant you, but in this image here, the bone cells would be analogous to the army of the dead, and the cartilage cells would be analogous to the orcs that were being defeated in this particular scene. And really, that's what's going on in with your bones. Okay, so we'll put that down for a second. That's going on in this epiphyseal or growth plate area. New cartilage is growing. It's being overwhelmed by bone cells here, but the bone lengthens as that process goes on. Now the deal is with when your growth spurt happens is that sex hormones, the estrogen, testosterone, speed up osteoblast activity. So at that time in your life, in puberty, the cartilage cells are proliferating rapidly. Well, the sex hormones are affecting the whole situation, basically speeding it up. And that's why you see incredible growth spurts at that time of one's life. You know, people tend to grow, males on average till they're 21, females on average till they're 18. That's on average, doesn't mean you're locked into that. But if you know those people that have grown extraordinarily in a period of time, other than their clothing not fitting too well, I'm guessing that if you remember that, if it was you remember your joints aching and sort of agonizing pain in particularly the arms and legs, but in many parts of the body. And that's because as the bone is growing, the muscle has to grow to accommodate that increased bone length. But it doesn't always do that, and so the muscles are being stretched and torqued, and there's oftentimes discomfort with those rapid growth rates. Okay, so hopefully that makes sense for what's going on at the epiphyseal plate, the growth plate in a bone. I'm going to go back to this first picture again here, because I want to point out another very important part. Well, actually, you know what? I'm gonna go to a different picture on the growth plate thing. I thought since we're thinking about it, I want to show you that. This is an actual human femur that I would use. I would show you in class if we had class. So this has been sectioned. It's been cut in cross section. It's there next to a keyboard, so you have an idea of the size of it. This one's been broken. It's had a hard life. So if we scroll down a bit, the growth plate is visible on the end of the femur. This would be that growth plate. It's still there, a remnant of it in this mature bone. Okay. Now in this one you can't see it quite as well, but there are two growth plates. The one down, the one for the shaft is a little less visible, this femur, but right here is the one that shows up pretty good here on the head of the femur. This would fit into the pelvis here. Okay, I'll see if it shows up any better on the last image I have here. No, I think it shows up best here. Okay, so granted it's not real evident, but that's the remnant of the growth plate in that bone. Okay, so then to go back to what I was going to talk about right here, In this artist's rendition, the growth plate is definitely more evident right here. Okay, but the other piece that I want to talk about is this flap of tissue right here. If I zoom in on it just a little bit, it's called the periosteum. And if I can just go right, there we go. Okay, the periosteum. And if you buy anything with a bone in it at the butcher shop, at the meat counter in the store, and you investigate this a little bit, and it's not dried out too much, you will find a tough covering on bones. It is called the periosteum. And this is where osteoblasts arise from. This is where osteoblasts are produced. This also contains blood vessels. But the thing that I want you to realize here is that this periosteum that covers the whole of the bone is actually continuous with the ligaments and tendons. So the ligament and or tendon, that ligaments are going to join bone to bone, tendons will join muscle to bone. If this were a point of attachment right here, there's a little bump on the bone, that's a common place for a muscle to attach. So if you could picture a muscle covering your elbow joint, so this is the lower end of the humerus, so your forearm would be down here, the muscle would cross that joint, and it would attach right there to the humerus. It's not just glued to that spot on the bone is the point. That tendon, the muscle, is connected by a tendon to the periosteum, so that the attachment of the muscle to the bone, yes, it occurs here, but it's attached to this incredibly tough periosteum that covers the whole of the bone. And so it's not just one spot, but that attachment is much more involving the whole bone than just that one single location. Okay, if I go back to this image right here, and I'm going to go up just a little bit more, I want you to notice, hopefully there's a good spot. Well, maybe I wanted to go down. I don't know you, but I get motion. There we go. That's the one I wanted. Right here, if we look at this femur, we can see the shaft of the femur. There's a marrow cavity. That's right here. And here we would find yellow marrow. We're going to find red marrow here. Okay. So yellow marrow is the fat. Okay. Actually, I'm just going to take a moment here, and I'm going to go back here, and I'm going to just Google marrow dishes. And that's to make the point that there are restaurants that specialize just in marrow dishes. So they'll separate the marrow out, and they'll cook it especially and season it, and some people just love it. I understand it's sort of has a buttery consistency to it. Hope you don't find that too disgusting. Okay, but that's what we find in this portion of the bone, yellow marrow. It's a place of fat storage. We find the red marrow here around we would call this spongy bone on the end of the bone. Okay, so yellow marrow here in the marrow cavity. This is what wolves and dogs and coyotes are after oftentimes when they're cracking bones, because that's a high calorie content substance right there. Red marrow, this is where blood cells are produced. Okay, so we would call this spongy bone. And compact bone, of course, is very dense, very strong, but it's heavy. So, you know, osteoclasts actually come along and hollow out the marrow cavity. And so the bone's weight is lightened by that marrow cavity. Then we have on the ends of the bone, we have red marrow in this spongy bone. Okay, and the spongy bone is obviously porous. It's lighter. I think I'm going to go up to look at another image just of spongy bone. That's pretty good. That's even, yeah, that's good too. We'll go here. So here's the spongy bone, and can you kind of picture patterns to the orientation of the spiny processes that make up spongy bone? We would actually call these long tendrils of bone, we would call them trabeculae. Not that I'm going to ask you to remember that, but that's the term for it. They are created. Your body is constantly remodeling your skeleton. And it's creating new bone oriented to support the movements that you do. And so if you do a lot of movement here that would be along this line, like this individual undoubtedly did, then there is bone oriented along that line to support that. If I go back to YouTube, again, hopefully the YouTube police will let me get away with this. It's not unlike Indiana Jones in the Temple of, or in the Last Crusade. And if you remember that, he's going to take the leap from the lion's mouth. He's got to step on the letters that spell Jehovah to get through the maze. And we'll just watch this little clip. Okay, so you see these little stony columns that were built to support the correct letters for Indiana Jones to step on. And that's the same as with your spongy bone here. There are these columns of support that are built by your body to support the movements that you do. Okay? There are no osteons, as your notes say, in these spiny processes. It's mostly matrix and sort of loose bone cells that are not arranged in an osteon. Okay, we're going to switch gears a little bit here, and we're going to consider bone repair for just a minute. So if I go back to images from your textbook, here we have an image of bone repair. A young man walking around with a cast on his leg. I always remember when I was a younger man, we used to play football on New Year's Eve with all of our snow equipment on, out on a snow-covered lake. You couldn't get moving very fast, so you didn't usually get hurt too bad. But it was just a fun thing that we did. One time we were playing that game, and my best friend and his son were out there playing. His son was, an early teenager, 11, 12 years old. Mark was his name. And Mark got the football, and he went running up the middle, and he got tackled after a short gain. And all of a sudden we hear all this screaming from underneath the pile of bodies that lay on top of Mark. We got him out from underneath the pile, and his leg wasn't pointed the right direction. So we got him up to the house where we were doing this by, and tried to get his snow pants off, but he wouldn't put up with it. He was just screaming. What we'd done is broken his femur. So his femur is his upper leg bone. Let's see, here we go, right here. Here's the femur. Okay, we'd broken his femur, and it displaced his leg. His leg was a little shorter. Those are two keys that you've broken a bone, particularly a leg bone, if the leg is shorter and if the foot is not pointing the right direction. It was, in his case, actually a good thing because he had a bone cyst there, a thin spot. So this is the compact bone that surrounds this, the marrow cavity. And on Mark's leg, there was a thin spot there that had grown or had not grown, and it broke that night. But because it broke, when his body rebuilt that bone there, it was able to repair that thin spot, that cyst that had grown there, and so in the long run was a good thing, even though it was painful, uncomfortable, and probably expensive at the time. So what happens? Well, you break a bone, the first thing that happens is a hematoma, which is a fancy name for a blood clot. Because the bones have a blood supply, that broken bone is going to bleed. If it's a break that pierces the skin, we call that a compact fracture. Compound fracture. Compound fracture. That's the one that breaks the skin, and you will actually see bleeding outside of the wound as a result of that. Whatever. So you get a broken bone, a blood clot forms in there to stop the blood flow. The next thing that happens is a fibrocartilaginous callus. That's fancy terms for cartilage, a tough cartilage that forms in there and starts to remodel the bone. That cartilage then, just like in bone growth, is replaced by solid bone, a callus in this place. Notice it goes across the entire span and plugs the marrow cavity there. But then through time, osteoclasts come along, gnaw that down, hollow that back out. That bony callus forms solid bone, but as is common, you'll continue to find a bump in the area where that fracture has healed. And I'm betting a number of you would say amen to that. I can still tell you where my bone broke. Doesn't always happen, but it can happen. Okay, then as promised, want to finish up with a consideration of cartilage. If we go back to the first image here, and I'll scale this back down to the original size, the ends of these bones, this humerus, is capped with cartilage, and that is common. Most of the bones of your skeleton have a cartilage end on them, where they intersect with another bone. That is kind of a wear pad, a lubricating pad. That might be here with the radius and ulna in the elbow region, up here in the shoulder with the humerus, here the pelvis where the femur comes in contact with it, the tibia and femur, fibula, all the delicate bones of the wrist and hand and of the feet, all of the bones of the vertebral column. You know that there are discs between all the vertebra. We looked at them last time, right there. Those all contain cartilage. And so if we look at cartilage, it's a little bit different than bone. So this is a look at a cartilage, a slide of cartilage. And if we take another look at some slides of cartilage, again, similar look. What I want you to notice is there's not a blood supply going out to it. If we look more closely at this, these are little chondroblasts or chondrocytes. A blast, that suffix typically means it's immature. A cyte suffix typically means it's a mature cell. So we had osteoblasts, which were immature bone cells, osteocytes, which were mature bone cells. Here we have chondroblasts, which are immature, chondrocytes, which are mature. Okay, but there's not a blood supply going to this, and so it's really that's why it's very difficult to heal cartilage. Many of you have probably torn cartilage, and have had surgeries maybe even on it. I'm going to give you a link to a cartilage repair surgery that I would like you to look at. The reason cartilage is so hard to heal is because it doesn't have a blood supply. Any material that gets, any nutrients and wastes that get exchanged with this chondrocyte have to diffuse through the cartilage to get there. Now, interestingly enough, there are procedures that will, and your body may on its own, sometimes build a blood supply network to an area of damaged cartilage and speed up the repair of it. Some people are blessed with an ability to do that, others not so much. There are surgical procedures that will encourage the body to do that. So cartilage is wonderful stuff. There are places all around your body where you find cartilage. Like your ear flaps, that's one kind of cartilage. If you look down at types of cartilage in your notes, we would call that elastic cartilage. It is made with, or it contains mostly elastin fibers. It's a kind of cartilage that is very flexible. Hyaline cartilage is the stuff that caps most of your bones, and that's made of elastin and collagen. So collagen makes it very tough. Elastin gives it a little bit of flexibility, but that's like your trachea. If you can feel your windpipe and even squeeze it, it's a rigid tube. Or your nose, the end of your nose would be that, and of course the end of your bones. There's also not, and then the last one is fibrocartilage. That would be like some of the cartilage in your knee. What I showed you of your intervertebral discs here, okay, that's another kind of cartilage. Those would be fibrocartilage. So the menisci of your knee is one that I'm going to show you a picture of. Well, actually, we'll just pull it right up here. And we'll zoom in on it just a little bit. So if we look here, this is the meniscus of the knee, okay? This is fibrocartilage. There is also on the end of the femur and on the end of the tibia here, hyaline cartilage. So there is two kinds of cartilage in your knee. If you were in class, I would, maybe even I'll get a picture of that if I can, or an image of it. I would show you a wear spot here. When people have surgeries, I've told you I'm always looking for extra parts. And Bethel's old librarian had a knee replacement, and I asked her for her old knee, and so she asked the surgeons, and they gave it to her. And so what they did is they basically sawed off the end of her tibia here, put on a new wear plate, and you can look at that hyaline cartilage on her old one, and you can see where this end of the femur has ground right through the hyaline cartilage and was rubbing bone on bone. Now, before it got through the cartilage, there are not nerves in the cartilage, and so you wouldn't feel that. But as soon as bone rubbed on bone, there are nerves in bone, and that's when it becomes very painful. Before that, she may have felt discomfort because this joint may have swelled up or been unstable and may have caused discomfort, but nothing like the pain that you get when bone rubs on bone. This is, so hyaline cartilage, this bone is capped with hyaline cartilage. This meniscus is fibrocartilage, and it's a very different kind of cartilage. And I'm going to put a link on Moodle for you to look at a cartilage surgery where the person goes, don't worry, it's not too gross. The person goes in and they surgically repair this. It's common for you to damage this meniscus and to have a flap of it sort of loose in the joint. And that flap can catch from time to time, give you a catch in the knee, or it can irritate the joint and cause it to swell up and be painful. And so this person has a torn meniscus, and the surgeon goes in and in one case removes part of it, and in another case sews it back into place. And so I think you'll enjoy that particular video clip. I hope you will anyway. Okay, so we're going to stop there today, and be sure to look at that link that I'm going to include on the cartilage repair. And we've got just a little bit to finish up next time on joints and some maladies associated with them. And we'll go from there. Thank you.